So, hello. First of all, I want to thank the organizers to give me an opportunity to talk about our research. And I will be talking about autoregressive model with double Pareto distributed noise, which is a joint work with Professor Agnieszka Błomańska. So let's start. First, I will present a short overview of our talk. So first of all, I will give a short introduction. I will describe the autoregressive model, the double Pareto distribution, and then I will show the estimation methods. And then I will show the Monte Carlo simulations of the method which was presented before. And finally, there will be a short summary. Okay. So first, we have autoregressive model XT defined by such an equation.
By I are functions or just scalars?
By are scalars because it is one-dimensional model. And we have ZT, which is sequence of uncorrelated random variables with finite variance and mean equal to 0. And this is known as white noise. And in classical case, we assume that it is Gaussian distributed. And then we have defined the double Pareto distribution, which is defined by such an density function and such a cumulative function. And then we have the properties of double Pareto distribution. Moment of order P of double Pareto distributions exists only for P less than theta. And this property is important because of the lack of second moment if P is less than 2. Double Pareto distribution belongs to the domain of attraction of alpha stable distribution, and the taste of double Pareto distributions behave power law. So then we define autoregressive model with double Pareto distributed noise. We assume that noise is double Pareto distributed. If theta is less or equal than 2, the assumption of classically understood lack of correlation of this model is not valid, and we can assume something more general, which is the independence of the components of the time series noise. And for simplicity, I will introduce such a notation. By AT, I define I define the xt minus pi x cubed minus 1 and so on and so on. And by dt, I define something like this, but I distract also 1 for this expression. And then I can define the likelihood function for this model. And the likelihood function is defined by this expression. And then we have log likelihood function, which is in such a form. And then we have the problem with finding the maximum of the function due to the component log of xt minus pxt minus 1 and so on. And there are two ideas to deal with it. We can use the Maclaurin series expansion and the Chebyshev polynomial expansions, and we assume this condition because then the Maclaurin series and Chebyshev polynomials are valid. So then we can, using the approximation, the Maclaurin series approximation, we have such an form, which is easier to find the derivatives because it is all polynomials. And to find the maximum of the function, we set the partial derivatives of the equation to 0. For fixed beta, it is possible to find estimates of phi j. And for formula, if we use this formula for Maclaurin series for p equal to 1, we have such an estimator of phi 1. And again, we can use the Chebyshev polynomials. We have such a log likelihood function. And then using the same methods as before, we have such an estimator. The estimator of parameter theta can be found without using the expansions. So we use the estimator known in literature, and this is in such a form. And then we want to also have we want to estimate beta parameter and p parameter, and for each possible value of beta, we calculate the residuals of the model, then calculate the empirical CDF of the residuals and compare it with theoretical, and calculate the mean squared error of the theoretical and empirical CDF. And we choose the model with the lowest mean square error. And for P, we use the same steps as for beta. And then we go to the simulations. Some preliminaries for it. We use the first 3 terms of Maclaurin series and the first 4 terms of Chebyshev polynomials. We compare our methods with generalized Euler-Walker estimator. And we consider AR1 model with theta 1 equal to 0.7 and beta equal to 0.8 and theta equal to 1.3. And we consider 4 trajectory lengths, 100, 500, 1000 and 5000, and run 1000 Monte Carlo simulations. And first, we see comparison of estimating by one parameter. We compare Taylor series expansion, Chebyshev polynomials, and Euler-Walker, and we see that our approach outperforms Euler-Walker in both cases. And here we have for n equal to 1000 and 5000, and we also see that our estimators perform better than the Euler-Walker approach. And then we want to validation for estimation of 3 parameter. We simulate the data from AR1 series and treat it as it was from AR2, and calculate the median of the estimated parameters and interquartile range to check if our approach is good. And we see that for all cases, the median is around the real values, and interquartile range is getting smaller with as the n is larger, and also mean squared error is going down with the if n is larger. And also for Chebyshev polynomials, we do the same, and is also valid. And then we use our estimator to estimate all the parameters. We estimate beta, theta, and theta, and phi, and we obtain such a results. We see that in case of n equal to 100, estimator of phi is nearly the boundary of the box plot. But for larger, if we get more trajectories, the estimators are more valid. And here we have for n equal to 1000 and 5000. And we do the same for the Chebyshev polynomials. We also see that the results are valid. And for longer trajectories, also we obtain good results. And going to the summary, we present 2 ways of approximating maximum likelihood function of ARP model with double Pareto distributed noise. The presented methodology was tested by Monte Carlo simulations, and the methods can be applied, for instance, to finance or industrial data with habitat behavior. And all presentation was prepared based on the paper prepared jointly with Professor Agnieszka Włomańska, which was accepted about 2 weeks ago. And this is this paper. And thank you for attention.